Steve and Marcus Horvath are identical twins. They share the exact same DNA, and they were born on the exact same day. But when scientists ran a deep analysis of their blood, the results revealed a biological anomaly. Even though they shared the same birth date, Marcus's body was biologically aging 4 years faster than Steve's. Historically, humans have treated aging as a rigid chronological countdown. In ancient Rome, the average life expectancy was just 25 years, a limit accepted as a basic fact of nature. Biologists now define aging as a series of interconnected cellular maintenance failures, occurring as damage accumulates faster than the body can repair itself. Scientists have finally figured out how to accurately measure that biological wear and tear, and early clinical trials suggest we might actually be able to run the clock in reverse. Decoupling chronological time from biological age reframes longevity as a solvable data problem. To solve that problem, we have to look at how cells fail. Every time your cells divide to replace old ones, the protective caps at the ends of your chromosomes, called telomeres, become progressively shorter. Eventually, they fray and leave your DNA exposed to damage. When that damage hits a certain threshold, some cells enter a strange state. They stop dividing, but they refuse to die. These senescent, or zombie cells, accumulate in your tissues and pump out toxic, inflammatory signals that damage the healthy cells around them. But the most accurate indicator of aging happens directly on the DNA sequence itself. Over the years, our genetic code accumulates chemical markers known as methylation. You can think of this process as a kind of molecular rust building up on the genome. To read this rust, researchers developed the epigenetic clock. They use artificial intelligence algorithms to scan 28 million distinct points of methylation on the DNA, averaging them all together to produce a single, highly precise biological age score. This precise scorecard solves a massive problem in longevity science. Researchers no longer have to wait decades for a patient to reach the end of their life to see if an anti-aging treatment works. They can apply an intervention and immediately read the biological response in the DNA. Certain environments naturally slow this clock down. Scientists look closely at blue zones, isolated global communities where an unusually high percentage of people live healthy lives past the age of 100. In places like Costa Rica's Nicoya Peninsula, a specific combination of natural diet, physical activity, and deep community integration actively protect cellular health, and it preserves those fragile chromosome telomeres. While humans are restricted by our biology, evolution shows us that extreme longevity is possible. The bowhead whale survives for over 2 centuries, relying on superior DNA repair mechanisms and cellular maintenance to avoid the diseases that kill shorter-lived mammals. Researchers are currently trying to replicate that level of biological maintenance in humans through clinical interventions. They are testing drugs called senolytics to selectively hunt and destroy inflammatory zombie cells, and using hormone therapies to actively regrow the thymus gland, the central control hub of the human immune system. This chart tracks the results of the TRIM trial, an experiment in thymus rejuvenation. In just 1 year, the subject's chronological age moved forward as expected, but their biological age scores dropped by an average of 2.5 years. These results prove that biological age is flexible, but treating a handful of patients in a highly controlled trial is one thing. Safely scaling these cellular interventions to the vast, complex ecosystem of the human body is vastly more difficult. Because early data is so promising, longevity research has triggered a gold rush. Tech billionaires are pouring hundreds of millions of dollars into secretive startups, searching for commercial treatments and unregulated wonder drugs. But treating aging aggressively carries severe biological dangers. If you attempt to completely reprogram a mature adult cell back into a youthful state, that cell can lose its identity entirely. It forgets what it is supposed to do, which can trigger uncontrolled growth and drastically increase the risk of cancer. Current research focuses on maximizing healthspan, the number of functional, disease-free years, rather than pursuing an indefinite lifespan. Managing aging will likely resemble the treatment of chronic conditions, using regular diagnostics and targeted therapies to maintain cellular health, much like modern cholesterol control. If science manages to push physical breakdown decades further away, people could remain highly functional for a century or more. that raises a fascinating question. How does a 150-year health span change the meaning, structure, and traditional milestones of a human life?